Um, yeah, so I'm just gonna also maybe post the YouTube link for today's session later in the chat so everyone can go back to the YouTube channel actually to review what we have covered for today. So I would just like to maybe give a little bit of a background introduction for today's session and why we're actually doing this material. So as you can see on the screen, so this is an effort to implement in fast linear algebra and machine learning applications in Python. So the theories and also the materials covered in these modules will be based on MIT professor Gilbert Strang's course and as well as his new books, Linear Algebra and Learning from Data. So everything that we're going to cover today and also how we're going to implement the linear algebra computation will be leveraged heavily on the way he does linear algebra and also benefit quite a lot from his perspective. But from what I have discovered that his like his theories in linear algebra doesn't really have a lot of implementation in Python. I can see that his course actually uses Julia language a lot, but then Julia language isn't really a popular language in the industry. And as everyone knows that most of the machine learning application right now are actually implemented in Python. So therefore, we will try to put out this effort to implement all these theories and as well as algorithms in Python language, and also try to do it in the most efficient way. So from actually his way of doing apply linear algebra. So he covered this concept first, which is the multiplication of a matrix by a vector. Even though this looks like a very basic and simple concept, but I guess it really has a lot of implication in a lot of machine learning applications. So the very direct derivation following from this multiplication is actually various matrix factorization. So so we all know the most common matrix factorization that are used in machine learning applications are definitely SVD, which we all know it refers to singular value decomposition. And we know that firstly, not only it is applied in recommender systems such as collaborative filtering, and because in that way you can actually come up with the data of a user product or uh, user item matrix, and then you can start doing matrix factorization using SVD that way. So you can get the user embeddings, right? So on the left, you can actually get the matrix that represent the embeddings of the users. And on the right-hand side, you can also get the embeddings of the items or the products. So this is the way that how in recommender system and collaborative filtering that you can use SVD to get the embeddings for users and products. But at the same time, in a lot of NLP applications, you can also use SVD to get to actually convert sparse matrix into a dense vector. So for example, when you are in a word term matrix, and then after SVD, you can actually get dense vectors for each of the word tokens. So that's another application of SVD as well. And also, as a special form of SVD is PCA. So you can also use it to do dimension reduction to visualize, um, to just visualize the relationship between data. So these are just some simple applications of SVD. So, but for today, since we are actually trying to go from the very beginning of Dr. Gilbert Strang's book, so we're just gonna firstly demonstrate the most simple matrix factorization in Python implementation. But before that, we would actually like to cover two ways of doing this very basic multiplication in Python. So um, as we all know, a lot of the data actually comes into like a relational table format. So a lot of the cases that in our day-to-day application, we actually use pandas. But then even though pandas can do vectorization as well, but we don't really recommend that because even when you use vectorization in pandas data frame, multiplication actually it wouldn't be the most efficient way, and sometimes it can be very slow too, as well as a lot of memory consumption. So today we will actually like to introduce two ways. They're like underlying technologies are all based in numpy. So the first way is that we are actually going to use native NumPy. So we are actually going to use a NumPy function to carry out this vectorization multiplication. But since we already mentioned at the very beginning that this effort is mostly way to implement Python programming actually using Professor Gilbert Strang's way of doing linear algebra. So as we all know, he would always like to approach this multiplication from the perspective of taking it as a linear combination of columns of the matrix. So therefore, there's no implementation in Python, in NumPy library to actually implement that way of computation. So today we are actually going to show you how you can do it that way in Python code. So basically taking this multiplication as a linear combination of the columns of A, and luckily, Python broadcasting computation can actually help us achieve that way. So we're going to show that as our second way of carry out this computation in Python code. And if we have more time, we are going to also touch a point matrix factorization as this CR matrix factorization as our very first matrix factorization series in the whole sequence of matrix factorization theories. So now we're just going to show some examples. So as you see that this is how you actually defined a multi-dimensional matrix in Python, right? So you're just gonna import numpy as NP, and then so this will be a multi-dimensional array, which will be the 3 by 3 matrix, right? So therefore you can see that actually it's pretty much just a list of lists, right? And then you're just gonna do another NP array wrapping around it, right? And then now that you see that B is also a 3 times 1 matrix, right? So this is how you actually define a column vector in Python, right? So now we can easily see that A is a beautiful 3 by 3 matrix, right? And then B is a 3 by 1 column vector. So, so the first method we're going to show is how you can actually carry out this multiplication in native numpy, right? So in Python 2, you can just simply call the dot function in numpy library. So so this is actually how Python 2 does all the matrix multiplication, regardless if it's if it's a matrix time multiply another matrix, or a matrix multiply another vector. So this is how you would call it in Python 2. But in Python 3, they actually changed it the way to do this. So they're just, so to do it in Python 3, for matrix multiplication, you're just gonna call A at B. So this way you can actually do any matrix multiplication easy and pretty. So I would just like to mention one point is that if you are going to carry out these computation in this native numpy way, you want to make sure that the just like you carry out linear algebra on the paper, you gotta make sure that the dimension order actually align, right? So as you can see, here's a 3 times 3 and 3, and the B is 3 by 1. So you gotta make sure that you define these numerical objects the right way, right? But I'll show you later that in the broadcasting way, this is actually not the case, right? So if you're doing the numpy, the native numpy way, you gotta make sure the dimension actually align as you do it on the paper, right? But in broadcasting, which is I'm gonna show you right now, it's actually not really the case. But like ironically, this is actually the way that in Professor Gilbert Strang's linear algebra book, this is how he actually does every matrix multiplication, by just taking it as a linear combination of the columns. But funny enough, you actually don't really need to ensure that the dimension order look the same as linear algebra theory. So I'm going to show you the specifics, how it is actually the case. So the second method right now we're going to show you is how you can actually take matrix multiplication as a linear combination of columns in Python. So the broadcasting way of Python can actually help in this case. So I would just like to mention 3 points under this topic. So firstly, what is really mean by broadcasting? So like it has nothing to do with the TV shows, right? So it simply just means that whenever broadcasting is going to happen is when you actually have two numerical objects, data objects that are of different dimension sizes. So in our example, the matrix A actually has 3 by 3 dimension, while the second numerical object, column vector B, is actually of size 3 by 1, right? So therefore, the B vector is actually of smaller sizes, right? So therefore, if you are ever going to carry out computation between these numerical objects that are of different sizes, the broadcasting underline will actually happen. And what it does is it basically just replicates it either replicates the rows over the columns, right? Like it either replicate the rows by itself multiple times along the column direction, or it will replicate the rows by itself along the rows, right? So therefore, um, and then then it will just convert the numerical object that is of smaller sizes into a size which is the same as the bigger numerical object. So this is what broadcasting does. And after it expands this smaller numerical object, then the computation will be carried out element wisely. So then because I would like to actually mention that just the whole point that we're doing these broadcasting and vectorization is that we want to avoid loops in Python code as much as possible because for if you're actually writing all these computation in loops, it's gonna really slow down your application by a lot. And then, but then funny enough, even when you're actually doing the computation in this broadcasting way, the computation is still carried out element wisely. So for that, I just mean that I will actually like to show you one thing. So for say, right? So what in, okay, just I'm just gonna use our example, right, to illustrate this. So so now we actually have a case that we want to multiply this matrix A by this vector B, right? So what we want to do is actually we want to like say we want to actually multiply the first column of A by the first cell of B, right? And then we also want to then multiply the second column of A by the second cell of B, right? And then also respectively for the third column as well. So in this case, rather than actually taking this multiplication for B as a column vector, we actually need to reshape this B into a row vector. So in that case, as you can see here, right? So then after you actually reshape this B vector, then you run this code, right? A star. So for in Python code, actually this star just means that you're gonna let the broadcasting happen and then you're gonna run the computation in an element-wise way, right? So you can imagine in this case, then after you reshape this B into a row vector, right? And then after you actually call this star um, arithmetic, right? So then what it happens underlying in Python code in the lower level implementation is just that like Python will just replicate this row vector B, right, 110 along the row direction, right? So then in this case, then it will be become 110 110 110. So right, so you will have actually the same row vector 3 times, right, along the row direction, right? And then in this case, then you can see that because the computation over here is actually carried out element wisely, then it means that just for every cell in A is actually going to be multiplied by every cell in this B after the expansion, right? So therefore, you can see then the result, the outcome then will just become that every cell of A will be actually multiplied by the first entry of B, right? Because it actually replicates itself in the first column, right? And the same thing happens for the second column and the third column as well. So then we would expect, right, our expectation after this computation then becomes, we should expect the product matrix, which that the first column of A should stay intact, right? Should stay the same. That because we're actually multiplied everything for the first column by 1. And then we should also expect that the same thing happens for the second column, right? So the second column in the multiplication product should also stay the same, right? And then, but we would expect that we're just gonna eliminate, right, the third column of A because we're actually gonna just multiply everything in the third column by 0. So not surprisingly, this is actually the case when you call this command in Python, right? So this is actually what you get after this command, right? So and then, but this is not not the end yet, right? Because this is just a scaling. This is just a scaling of all the columns of A, right? But then we still need to take because this is just like a weighting of the columns of A. Then we have to take the sums, right? So because it will be the weighted sums of the columns of A. So therefore, the Python command to do that is actually using, because, okay, so this way right here up to here is actually the scaling computation, right? Using broadcasting in Python. And then, so this is actually the matrix that we achieve at this step, right? And then you should just call dot sum. So and then you actually have a parameter to put in this function, this sum function, right? So if you are going to actually sum like so what we do is actually we need to sum it this way, right? Sum the columns, right? So therefore its axis equals to 1. But if you are actually summing over the rows, right, then you would just put axis equal to 0, right? So therefore after this command, right, so you can see that when after you sum over the columns, you actually get 3 by, no, you actually get a 1 by 3 vector, right? So which is summing over, but this is exactly the same as the native numpy result, right? Which is 3, 4, 12, but just differently that the numpy way, it's actually consistent with how you carry out the computation on paper. But this way, because we actually do it in the broadcasting way, so you just need to transpose this row vector into a column vector, right? But theoretically, you actually get the same result. So yeah, that's actually, so these are the two ways of actually carry out these computation in Python code. So both of these ways are actually avoiding doing all these by loops, right? Like for every cell, and then it's actually doing it in a vectorization way. But just differently, that the native NumPy way, it's just treating this multiplication as the traditional way, which is just, taking every row of A, taking every row vector of A, and then having a dot product against the B column vector, right? But since we want to actually do it the smart way as Professor Gilbert Strang, so therefore this is our broadcasting way to implement this multiplication as a linear combination of the columns of A, right? So I hope that, like, I guess in reality, in the real world application, like you pretty much can take either way to do it fast, right? So that is the very, just the introduction of the very basic multiplication for the matrices. And then for the next one, we're actually going to introduce the very first matrix vectorization, which is the CR matrix factorization, right? So this CR matrix vectorization, it actually has a lot of implication to subsequent SVD factorization, right? Um, and the theories just goes as the matrix of A is, you can just factor any matrix of A as a multiplication of the basis matrix of its column space, and then times its the basis matrix of its row space, right? And um, interesting enough that the basis of the row space, right? It's actually happened to be the row reduced echelon form of the matrix A, right? So, and then we're also going to show how you can use Python code to actually find all of these, right? So, not only you can actually find the basis matrix of column space of A, at the same time, you can also easily to get it for the row space, right? So in MATLAB, they already implemented as a function called RREF, right? So if you have taken numerical linear algebra in university, you probably already know that. And then we're going to show you today that in Python, you also have something similar, right? So this link is actually MATLAB implementation of this CR factorization, right? So this is, so if you're interested yourself, you can just click on and then you can just go to this website to take a look at this MATLAB implementation. It's nothing that complicated. So this is pretty much how it is being done in MATLAB, right? So you just take the two, like parameters. This is actually the return, right, of your C and R. So this is the output of the two factored matrix, right? And then you're just gonna take this matrix A as the parameter, right? As the parameter of your function. And then you're just gonna call this MATLAB function, right, RREF. And then we're gonna actually show you that you can actually get this function as well in Python. So the trick is the library called the SymPy, right? So you have numpy and then you have SymPy. So numpy is all the basic vector and matrix operation, right? Doing it in the most efficient way. And then some SymPy is actually one level up, taking advantage of all the numpy numerical operations and actually get to the linear algebra operation, the more complicated linear algebra operations, right? So these operations are all included in this library called SymPy. So if you call from SymPy import star, which means that you're just gonna import everything from this library, right? And because we actually defined our matrix A in as a numpy object, right? So what you need to do, the first step is actually to convert it into a SymPy object, right? So therefore, because this matrix constructor in SymPy is just a way to convert any numpy matrix into a SymPy matrix, right? Then after you convert it into a SymPy matrix, then you can actually call the RREF function in SymPy, right? So there you get the result, right? So this is actually the row reduced echelon form of matrix A. And it also happened, so you can actually the first two row vectors just represent the basis of the row space of A, right? So because you can see that here the number of independent row vectors, right, for A, the number is just 2 because the third row just contain no zeros. So therefore the rank of the row space of A is actually 2. So therefore you only need to take the 2 row vectors, right? And that is actually your matrix of R, right? So this is how you actually get the row, the matrix which contains the basis vector of the row space of A. So this is the R that you will get. And interesting enough, you can also get the same thing for this C factored output. So, and then you can also use that in this SymPy library as well that can help you achieve that. So I haven't actually showed it here on this module, but I can actually just maybe say it out that to do that, you can just call matrix of A and then call column space square. So that's actually the function to get the column space of this matrix. So yeah, so that's pretty much what we would like to cover for today. I think it's pretty straightforward. I don't know, like if you have any questions or comments. And then for the subsequent sessions of our working sessions, then we will actually move along. We will actually move along Professor Gilbert Strang's book. So I'm just gonna actually show you that his book is actually called Linear Algebra and Learning from Data. So I believe